to continue, today we going to talk about, so we'll start talking about, I'd like to talk about slices and relations in quantum groups. It's the first, this is continuation for something we discussed, started last time. And so this is when first, so suppose I have a quiver, I'll just draw some quivers, so I have some vertices and some dimension vectors, maybe V1, V2, V3, and then there's framing vertices. I can do them in a different color, in fact. So first dimension vector W1, W2, W3, and then I have all these quiver maps. So maybe there's a loop here, and this loop comes with its opposite loop. Maybe I'll draw it the other way around, and then there's maybe two arrows here, and the corresponding opposite arrows, etc. And then, of course, they're framing. So when you first see this maybe the definition of a quiver variety may look a little arbitrary, and it's just certainly possible. But in fact, you should think of this as belonging, so representations of a quiver. I mean, that's one way to look at it. So representations. So this quiver data. That's just really, this is representation of a certain algebra. Just write an algebra in which the generators are arrows. Generators are, so every arrow is some element in my algebra. So in fact, so this algebra is kind of like a quotient. So this is the path algebra of quiver. The quiver Q. So this is my quiver Q, and I have modular relations. So generators in this path algebra are just arrows. So every arrow corresponds to generators, and compose if they can compose if you can compose the arrows. So this is, and then relations. They're given by the moment map equation. So now you may ask, so here we have vertices of two different kinds, and it's slightly inconvenient to have vertices V, special vertices V, and also separate framing vertices. And this can be well, if you think about it, these arrows, they don't. You can guess if you think about it as a filler that contains no meaning, you should think about everything, but in particular about this instance here. So if you have if we consider this framing arrows, it's the same as if we took, that is, the data is the same as if we took all this data and instead of having this framing vertices and one arrow from it, we could unite all these framing vertices inside into one, so maybe we'll call it just one vector space. It has dimension v naught associated to this equal to 1. And then here, instead of having a map from W dimensional space, I can have just some number of arrows. So here I put the number of arrows is here equals to is this W1 and so on. Right? So that's just exact same data. So that is convenient. And so then, so if I have representations of an algebra, so then if I have a if R maybe is a representation on algebra A, then associated to this I have first the endomorphisms. These endomorphisms of R home as a modules. Well, I'm not gonna keep the A modules from RR. This, of course, this tells you how big is the space of automorphism of this object. So invertible elements, there are the automorphisms. Then the deformations, and the deformation, first order deformations, this are so in here, see the automorphism. So if I look at the inside here, see the automorphisms. And what would that gonna? And so then the first order deformation are given by the X1. And then there will be this very abstractly. And then the abstractions to this first order deformation. So if I have, there's on first order deformation, there is a map, abstraction map, that tells you whether the first order deformation can be continued to a second order deformation. And this would be, this map, the target of that map is in X2. And in principle, there's somehow so on, but this is not going to be the case for us, because the kind of deformation, the kind of representations we may consider representations with delta I, which is called delta I representation. So this is a representation in which, so this would be a representation with, so a representation of my algebra is a vector space at every vertex and a map between them with the vector space, we call it C, whatever your field is, at the ith vertex, and all maps are Ziller. And then it's clearly home if I have representation which is some multiplicities, if I consider representation, I apologize, if my representation is some multiplicities. Multiplicities are just vi delta I, then home RR, those are clearly irreducible. I mean, it's clearly an irreducible representation, and there's somehow nothing can be said about it. So that would be just direct sum of GL VI, right? So this is the Lie algebra. This is the Lie algebra by which we take so this is, so inside here, there's a product. The invertible elements are this GLVI, and this is, well, there are scalars that correspond to the zero vertex, but the scalars are automorphisms of every representation. We will not let's make this mental point to ourselves once and don't repeat it more. When you talk about representation of algebras, all of them have scalars as endomorphisms, and so for us, since we have that special vertex of dimension 1, we normalize the automorphisms so they don't act at that vertex. That's the easiest. So this is this is the group by which we take a quotient. These are automorphisms. Now, if I want to compute the Ext in my algebra between the ith representation and jth representation, well, the dimension of that, it's clearly, so this is the definition of an X. What's an X? X means you count modules in which a sub is one and the quotient is the other. And so the only possibility is you have one non-zero map for the home. And so this is just the number of errors from the ith vertex. So number of errors that go from the ith vertex to many colors here. So from the ith vertex to the jth vertex. And this is X1. And in fact, we observe the duality. So this is a vector space. So this is a vector space of maps between ith and jth vertex. So we observe the duality that X1 from delta I delta J is the same, maybe dual with Ji. Sorry, there's very little logic in renaming the indices, but so this is like H bar inverse. It has a weight because this is the dual space. Arrows going one way are the dual to the arrows going the other way of the X1 delta I delta J, the dual space. So this would be, for our algebra, this is a special case of Serre duality. So this is, and then the abstraction map. Well, that's just the moment map. Something you have to convince itself, but it's the moment map. So something observe that if I have if I believe in Serre duality, that X2 from a representation to itself, that would be H1 times X times the home. All right, so this lies in that's exactly the space in which so this is where that's again the Lie algebra of GLV, and this is where if I have in the first order deformation, if I assign this arrow as arbitrary, okay, I can do that. In the second order deformation, then I have to make sure my relations are satisfied, and well, the relations are quadratic, and the abstraction map is quadratic, and so they have to be more or less the same. That's something here. So we decided that this is the quiver representation. So my quiver variety well, it's more or less, well, it's a, well, maybe not, it's a stack. So maybe my quiver variety is some. That's my quiver variety. I define my quiver variety as a quotient, so it means it's a substack. It's an open set of some stack. So I had this kind of stack of quiver data. Plus moment mob equations. Modulo my group GLV. And that is the stack of representation. My algebra A. And in fact, I'm in the neighborhood, the point 0. It's kind of the, right? No, sorry, not the point 0. And then I can describe, or not I mean people before me could. It's not the. I'm explaining something which is kind of really old. You know, how much traveled road in theory of moduli, how I think about moduli of sheaves or modulus representation of algebras. So we had this map here had a quiver variety X. This is quiver variety X. This had this kind of blow down map X naught as a singular, this kind of single variety X naught. Which was the quotient, the ordinary affine quotient. i.e. stack of invariance. And in terms of representation of algebra, what does it mean? You consider so this is the points in it. Points in the affine quotients are closed orbits. So points. So when you have a group action, then in every fiber, so if you look at the group action, you look at the invariance. In every fiber of the map to the invariance, there will be one and only one of the reductive group and an algebra. If you have a reductive group action on the affine variety, then the invariants separate closed points. And so in every fiber there will be unique closed orbit, and that's the representative. That's the representative of this blowdown here. And so this would be, and in terms of this would be, when is the orbit closed? Is that these are semi-simple representation. And this is this map here. Let's just take a representation. So every representation up to has a filtration with irreducible quotients. And this filtration is not unique, but the up to the ordering, this direct sum of the direct sum of this quotient you take, this is unique. So this is semi-simplification. Or another way of saying, you take representation and map to its K-theory class. So if you have filtration, you just kill it. And so here we were talking about. So we had this kind of mental picture here of this X naught, and this X naught had this action of H bar that contracted everything. So maybe H bar inverse is the weight of this arrow, contracts everything to a single point, and that point is where all the invariants are 0. So this is the 0 point. This is 0, and in this sense, this is my representation. When my representation is, this is the point where my representation is a direct sum. Maybe equality is not the right thing. So maybe I'll just write kind of corresponds to 0. Or other people called null cone. This the set where all invariants are 0, and so this corresponds to representation is direct sum. Is multiplies this vi, this representation delta. I starts with from 0 to whatever, to however many. Okay, and so this is the fact that this puts us in a kind of a general framework that if I have an algebra roughly of this kind, then so an algebra which satisfies a third duality of a certain kind, then, well, of the kind which is specified, then the moduli space of representation of that algebra will look in the neighborhood of any point like the quiver variety, or I mean at least quiver variety is very so. In fact, quiver varieties are not something very esoteric, and it's quite the opposite. It's the quiver variety very representative of what the moduli space of like shifts on K3 surfaces, another moduli problem where you have this sort of third duality, then this is the moduli space is going to look like, at least in the neighborhood of a given representation, they're going to look like this moduli space is going to look like quiver varieties. And so in particular, we're interested in the situation where in this singular variety, we now specialize. Slice happens in the situation if we specialize the current variables then what can happen is that this, maybe in the particular example we had at the end of last lecture. So if I really think about T star P1 example, then the weight of these two directions are like U times H bar inverse and U inverse times H bar, or maybe A, let's call it A inverse H bar inverse and A times H bar inverse. And so if A takes a special value, we can have a fixed point. But other than 0. So we can have a point, like this, for example. If A happens to be H1, right? So this is. And so this preceding discussion says that in the neighborhood of that point, so maybe call call this, since we're talking about representation, let's call this representation R. Sorry, this would be confusing with the R matrices, but I already started talking calling it R, so maybe somehow no, it's too late to so this representation R. And so concretely, for example, for instance, to have a slightly non-trivial example, what could be e.g. for the quiver with one loop, what could happen? So if I have, so this is my, so suppose I have quiver with one loop, and then it has, maybe this has the weight A1, and I have a map 2. So this was the I start with the quiver with one loop. So it means I have some dimension vector here. Maybe I'll just draw this vectors as kind of dots. So maybe actually I didn't prepare this part how to draw this vector best, but maybe if I draw them again as dots, I hope it's not too confusing. So it means this dot will now become a bunch of dots. They all sit inside. They're all vectors within a vector space. And then here my W equals 2. So I'm going to have something two-dimensional here. Maybe I'll put that two-dimensional object here. And so I decided my covariance weights on the framing are like A1 and A2. And so now suppose I have a non-zero arrow here, then so maybe let this arrow have weight T1. So if I have a non-zero arrow, it has to go, since the arrow has no action here, it has to go to the same weight A1, and then this T1 arrow should take it to A1 times T1 inverse. And the reason it has to go to T1 inverse because it has to be invariant, means the arrow has weight T1, and then also gets a weight from it gets the weight of the target divided by the weight of the source. And so this whole combination has to be 1. And so this is how I get this T1 inverse. And then I get, keep going. Maybe eventually I get to a vertex, which is A1, T1, 1 minus n. And then I get here, this arrow now has the weight, 1 over T1, T2. And so this A2 better be the case that this is A1 is equal to this arrow has weight T1 times T2 because it had to be the case that this is T1 minus n T2 minus 1. And so that's a picture. That's a picture of invariant representation. So if I have this condition like that, that's an equation on my current variables that tells you that if I specialize the two evaluation, if I specialize the, so this is if I'm thinking about kind of Fock space, Fock A1 tensor Fock A2 will not be reducible if this happens. Right? It will be not irreducible because if I have, well, we'll talk about it in a second. Sorry, I'm a little bit ahead of myself, but so that's okay. One can go back in this discussion. And so just on very general ground, if I have this fixed representation, then I can look at the neighborhood of this fixed representation. So this would be its neighborhood. Neighborhood of R, both and its preimage in X will look like by completely general grounds will look like. So this is why this discussion was. This is the purpose of having that discussion. Will look like equivariety for what? So for the quiver given by you have to compute. So if I take R, if I write R as a direct sum of Ri, and these are irreducibles, the sum multiplice, so irreducibles. And then this would be, so this is, I have to look at X1 between this Ri, Rj. And so this would be, I'll have my vertices labeled by the reducibles. I have my edges labeled by the X1s between them. And so otherwise I'll have just a quiver. Okay. And the point is that this, so since they're irreducibles, then we know, right? I mean, the number of edges you're gonna get is the dimension vector is some maybe with some multiplicities. Sorry, with some multiplicities. Mi. And how about I just denote them Vi? Vi prime Ri. These are irreducibles. And this is the new dimension vector. Previously, dimension vector, where it came from? It came from the fact that we had this delta function, the representation repeated a certain number of times. And so now it's some reduced representation repeated some number of times. And so so incidentally, this representation is reducible, right? I mean, because you can take any vector here, will eventually come here, and then we'll somehow cycle here, right? So if we have anything non-zero, that would be by acting on by my arrows, I can make it come to the. This is one-dimensional space with a certain weight, and then if I have this representation is reducible. And so so this tells me the no dimension vector comes from multiplicities of reducible representation. In my case, that would be this would be and then this X. So what about this X? This X we can compute this. The point is that we can compute in just in K theory. The character of that we can compute in K theory of my algebra, because just from characters, I was computing characters, compute just from the characters means that because the X0 and X2 we know, and the rest, and so this would be X1 computation from just the Euler characteristic. So in other words, in K theory of any algebra, there is this pairing, just the Euler characteristic of. So now you compute there's a kind of pairing, Euler characteristic of kind of R and R1 and R prime, and it's the alternating sum Xi R prime. It says this depends only on K theory classes of these representations. Doesn't depend only on characters. It doesn't depend on what the actual representations are. And since we know these guys are irreducible, that means that we can compute this X1 just purely from characters. And so the result would be that so this is an exercise. Suppose So we have one special vertex with dimension 1, and then all, because V0 had the special vertex and all the other vertices. And suppose my representation R has the following property. It uses, there's a representation that uses that special vertex, like in this case. So R is some representation R0 plus some summation. Just get plus sum of delta functions, so delta functions with some multiplicities. Delta I, so this I is not equal to 0 because we already used the 0 vertex, and this is representation. This has dimension. So this has a current character. So dimension, you here in this business, you compute all the spaces carry group actions. So when you talk about dimensions, you might as well just put the character as a current dimension. Maybe call it 1, and then some dimension beta. So this would be, this is the 0th vertex. We use it, and some beta. And in our example, this means this is this space. This is space. So this means in our example, this beta is this A1 times 1 plus T1 inverse plus T1 1 minus n. And this is okay. Then, so this is an, so then this quiver is the same. Up to loops at the 0th vertex. So this is, if I have the 0th vertex, in principle I could have loops there, but they don't participate. Those are just a vector space. Those are just numbers. And this loops at the 0th vertex, they have the meaning that these are just they tell us in this picture that this point is free to move here or there. And there's some degrees of freedom that if I move that point where I consider the slice, then somehow nothing happens. And those degrees of freedom are there's some direction in which nothing, there's some stratum. In other words, if I have this this representation I'm considering, there's some degrees of freedom. They don't change anything, and those corresponds from loops at the 0 vertex. And this is coordinate vector space. This is a vector space. So this is, and this is coordinates along the stratum containing R. So here. And then the new dimension vector is V prime. That is that V prime. And the new framing vector is the old framing vector minus H bar times the Cartan matrix times that vector beta. Or the Cartan matrix of my quiver, that's just a matrix which has the properties. So this is that's the matrix which is like 1 plus H bar inverse minus the adjacency matrix my quiver. So this is usually cut-down matrix is like 2 on the diagonal minus the number of arrows. So that's so instead 2 becomes 1 plus H bar because we have cut-down matrix. This cut-down matrix that records X. So this cut-down matrix records the Euler characteristic of delta I delta J. Right. So if I have the two representation, then they're gonna get what's it gonna be? If I have this reducible representation delta I delta J, I'm gonna give each one of them has a home from itself, has an x2 from itself. So that would give me 1 plus H bar. This is from the home. This is from x2, and this is from x1. So e.g., if I consider the quiver, if I have my e.g., if my quiver is kind of A2 quiver, A2 quiver, then the Cartan matrix is 1 plus H bar inverse, 1 plus H bar inverse. Here I get -1, and here I get minus H bar inverse. Or the other way around, depends on how you orient the thing. Or if I have my quiver like this, so A0 hat quiver, then the Cartan matrix becomes 1 plus H. It's just a one number, H1 inverse minus T1 minus T2, and so that would be, if I remember what's H1 inverse, it becomes 1 minus T1 times 1 minus T2. It's a number. So this has two vertices, so Cartan matrix is 2 by 2, and this has one vertex, so Cartan matrix is 1 by 1. And so for instance, if I compute if my beta is as before, so if beta, my quiver, if for quiver, if beta is as before, so this has A1 times 1 plus T1 inverse plus T1 1 minus n, then the new framing would be, well, it's a you'll see this will be there will be some cancellation, and so this would be T2 inverse, well, A1 T2 inverse plus T1 minus n. And so the conclusion says that if restriction to the neighborhood of a slice give me a map from Fock space Fock A tensor Fock what was it, A times T1 minus n T2 minus 1 goes to Fock A T2, and T2 moves across. So I get T2 minus 1 tensor Fock A T1 minus. So now I have to be a little bit specific about the order, and I'll discuss in a second. Order important here. So this depends on whether you talk. So the order will depend whether you talk the modules or the dual module. But the geometry is totally on top of that. So this is maybe. So this is. But we didn't discuss what it means. In other words, there's a coproduct and there's opposite coproduct, and so one has to discuss this, and we'll talk about it in a second. But so why is there this correspondence? Why is this intertwined, the action of my quantum group? So I remind you that the action of my quantum group was acting by correspondences, and the correspondences act. So all my correspondences stable. All my correspondences come from stable envelopes. Our correspondences over this kind of, this so to speak, affine quotient. And so then I had that. Right? Like for instance, when we talked about the action of how did the action of the quantum group been constructed? We took some x, had some dimension vector. Let's come with some number. So maybe it has some dimension vector beta and some framing w naught. And then we wanted to act on x with dimension vectors v and w. And then we embedded this sits at the fixed locus inside representation space where we add this whole dimensions. So then I'll just write there's some kind of, so if I have the stable envelope, so this is a stable envelope with correspondence when you get beta plus v and then w plus w. And then a K-theory class, we can further restrict to different components. So that we can take restriction to a different component. So a different component would be where all of the, so this would be, I'm running out of space here, maybe I'll write it like this. You go to beta plus v w, and then there's another component which is kind of x cross 0 times v naught, and this is a point. So this multiplying by a point. Right? This is a typical kind of thing that how one constructs its correspondences. And point is that all of that happens with over. So means we have when there's a corresponding map here of x naught, kind of x naught cross x naught going to x naught. This covers, and so this is when you take direct sum, that means the corresponding reducibles. So this is x naught remembers the simplification of representation, and that's just, this map is just at reducible. Right? So this is just, so x naught is in my language is a variety that parameterizes semi-simple representation, and semi-simple representation I can add. And so then, but that's reducible. That means that here we can, the whole, when we construct the quantum group, we take coefficients here in this part. So here. Take coefficients. But the entire K-theory, so this space, it's a whole space, but it can be contracted. This contracts, of course, to the neighborhood of the zero fiber here. So that we have, we can take the 0 here, and then this space, of course, contracts to the preimage of 0. Right? So this is the central fiber, because okay, well, we have this H bar action, and the whole space contracts to the preimage of the neighborhood of 0 here, and then here's 0 representation, and then here we can get a point which is some fixed representation. I think we call it R. So R, if I have an interesting point, which we call it R, direct some kind of 0, headed up by 0. For us, the 0 representation is always the one that's it's the direct sum of this delta function representations. All maps are 0, so that's the 0 representation. But it can have different dimensions, and we pad it up to give it somehow. It's a 0 with a certain dimension. We pad it up by 0. The point here. So here we can look at the neighborhood of this point. Can look at the neighborhood of this point. And then so this as representation, well, just going to be R plus 0, right? The zeros were dimensions of 0z, but we can. That's correct. So if we look at the how my correspondences work, that will take a neighborhood of a point I'm interested in, and take it to the neighborhood of a point I'm interested in. So that is preserved by my actions. And if I restrict to that neighborhood, that's an equivariant map. So this is why. So restriction to the slice. The neighborhood has the preimage of that neighborhood is called has the name the slice. So restriction. So the conclusion, kind of important conclusion. Okay. So if I specialize my variable so that I get this, so that get a non-trivial fixed representation, then I get an actual map. So in fact, and a map is always the way it goes is always if I look at ordinary case here, ordinary cohomology, then the restriction is a pullback under restriction is a map that goes from the ambient space to the slice. Okay. And so maybe it's speaking of the order. So I guess speaking of the order of the, so it's good to have it's good for maybe it's very, I'm running out of time, but it'd be good to think about the following example. Take we can take the Yang this whole discussions work for any cohomology theory. So like you take the Yangian of GL2 acting in C2 evaluation kind of A1, C2 evaluation A2, where so this is by so this is like the cohomology of the fixed locus. You take the DG and then you take the fixed locus, and then there's a stable envelope map that goes to the cohomology of the whole Grassmannian size 2. Right? So this is both stable envelopes by construction of the maps of Yangian module. This is a Yangian module, and this is map of Yangian modules. Right? And so let's think about the situation when there is some resonance. So in general isomorphism. But now suppose we have a resonance. So what is the resonance? So suppose I have my favorite picture. Let this be A. This A could be like, for example, could be A1 minus A2, depends on your conventions. And then this will have the weight. I'm writing a homology, so this will have the weight minus A minus H bar. This will have the weight A plus H bar. And so when one of those guys is 0, then I get a resonance. So I have, suppose this guy is 0. It doesn't matter. Suppose this one is 0. Suppose this is 0. So I get a fixed point of my torus on this downgoing thing. And so then I can talk about the stable envelopes, which are for which this weight is positive or for which this weight is negative. So let's say this stable envelope so let's say this is this weight is 0. And so then if this weight is repelling, let's call this step minus. So this would look like this. This is step minus. And then there's also step plus, which would look something like this. This is the step plus for which this 0 weight is attractive. And so then I have maps from the cohomology of fixed locus, which is in this case C2 times C2. I have a map step minus, and I have the map, and then the inverse to the cohomology of my TG2. And then the inverse map, we know the inverse map is you take the step, the opposite step, and take its transpose. So this is one possibility. is the other possibility, that you can have this map, you can consider the stop going this way, and the transpose is the opposite way. And so it is exactly in one is with these diagrams. This would be there'll be a problem. And so if we look at here, it's this one. So this will not be surjective. So minus this goes to 0. Slice, right? Because we take a slice at this point, and that step entirely misses that point. So this is misses slice, i.e. not surjective. Because it like I said, with the slice of this we restrict to a point which the cycles just miss. And then the conversely, step plus transpose blows up, because so what does it mean transpose? Transpose means integrate. So we integrate along a direction that has 0 weight, because integrate push forward along a push forward along directions. I'll just write improper push forward. Means you push forward along a direction which is not compact, means you have to integrate along this direction. What does it mean to have transpose map? It means you integrate. And then you have to integrate along the direction that has 0 weight, which is non-compact, has 0 weight. So you get that. I mean, once if you compute it correctly, that integration will have that 0 weight in the denominator. So that blows up. Whereas by contrast, this perfectly fine. This both maps isomorphism. And so this right. And so the conclusion is that this, in this kind of slice business, it's always so one observes. So conclusion. This, if we take this cohomology of this whole space, TG2, if I'm in a situation when I have an invariant direction, then it always have something. This is one-dimensional representation. So this is my slice map here. And the kernel is 3-dimensional. This is always. That representation is always has breaks up in this way. Whereas if I take C2 times C2, this breaks up. You can get either 3 and 1 or 1 and 3. Depending on the order. So this order in which you remember I said there's a certain order. That order in which you get the correct intertwining relation comes from considerations like that kind. Okay. I mean, you can put it differently. So this is if this guy splits up in a, this is we discussed that the dual to the stable envelope is always the other stable envelope, and so these representations are really, these two representations are always dual. And so if I have a representation with one-dimensional quotient and three-dimensional sub, then dual will have the other way around. And but this representation is generally irreducible self-dual, but then at a certain point there's a difference between cohomology and homology. So if I have an inclusion, then homology maps one way, cohomology maps the other way, and so that's the difference between the module and the dual module. So the dual module, the cohomology will be homology. So okay. So now I'm as usual. I spent the whole time on clarification something which was supposed to be left over from previous lecture, but right. So sorry, I forgot to say the most important thing. So question. So there's a conjecture. All relations in our quantum groups come from slices. So this is first discussed in Q quantum groups quantum cohomology. And so true for the Q-root of one loop. So discuss this is the fact is like it's enough to check, of course, since by deformation it's enough to check for the Yangian, right? Because if I have, so what does my quantum group look like? My quantum group I defined to be basically in terms of matrix elements of R matrices, and so the relation comes from operators that commute with my R matrices. Now, if I have it means my relations, if I perturb the R matrix, it means my generators will only go up and relations will only go down. And so if I have something at a special point, I decide that in fact the relations exactly match the generators, then I'm done, because it's the perturbation, they go right, this perturbation argument. If I know by definition all my generators deform, and so how I define the final group, defined as so that all my generators deform, and so it's only the question that relations deform, and the slice relation obviously deform because the slice relation just abstract relations in cohomology. So that would be this kind of pullback argument works in any cohomology theory. And so it's enough to check this for Yangian, and this is for Yangian. Again, it's in QGQC. It checked explicitly that this reproduces in the end. And in fact for the generations, in fact for the Yangian, in fact it's enough to choose a special point at h bar equals 0, and so this would be, and this gives you in here's checked. So this just gives click relation. And so in particular the quantum, so this become, in this case, we discussed. These are screening operators. Slices. You can identify slices with the screening operators. So you can not only you can have a kind of a topological description of what the relations are, but you can also write it in terms of if you have some kind of Virasoro, Q-Virasoro, whatever elliptic Virasoro, how are you going to think about it? Then you can there's some operators you can write that commute with it, and those are the screening operators. And so towards this conjecture, so what is known, we know by different means. We'll discuss some maybe that deformations. Generic of that. So at least it kind of that's some argument you can use. And also it's known that this is towards this conjecture it's known. So there's some paper I've been writing with Nakajima for many years, and one of the results of this paper should be that so I hope he so there's some kind of one of the main results is that it's not the main result, but it contains there that if there is no if the fixed locus if 0 is the only fixed point fixed representation, then this representation then kind of whatever cohomology of some x over all v, and this representation is irreducible. And there are some other results of that kind. So, but so that would be another. So if there is no slice, there's no slice available, then the representation should be reducible, and in fact, it's true. So that's another thing. I mean, there's some discussion. Anyway, I think this would be some if somebody thinks that they should think about this circle of not the circle. I hope it's not a circle. Maybe this avenue of research, not a circle of research. I hope it has a definite direction. And so I kind of think this is an interesting circle of questions to investigate in general. So this is right. And now, as usual, we come to what I was actually gonna say in this lecture. And okay. So this will not be a smooth transition. I apologize. But so last time we saw a quantum integral system. Of the following kind: you take the trace formed by the operators in which you take the trace over the first factor. You put in the first factor. You put some operator z times r1, and we put r1, 2 of whatever a1 over a2. You can take it like that. And this is an endomorphism. This is some fixed operator. that under Z commutes with R. And this is, maybe I'll just name it A. That a variable. So this is an endomorphism. This goes endomorphism of the second factor. Kind of functions in A with valid endomorphism of the second factor. And so then, this is, so this commute we discussed this commute for all A and fixed. Is that? And so then, in an example of such that, so this is an example, e.g., principal example of such that, Z could act by kind of product. That can act by product of Zi to just dimension vectors. It just records dimension vector. And that, of course, since the R matrix preserves the sums of dimensions, that would commute with R. So this implies. So this is such that this is 0, and this would be implied by that. So R commutes. And then we took what we did. We took for Z equals 0. These are vacuum matrix elements. And we discussed the vacuum matrix elements. These are the operators. So this becomes operators of just really multiplication in whatever cohomology of X, KC of X, what's the cohomology? So all of these are either algebras or have shifts of algebras on them, and there is an operator which just multiplies. So this commute. Since we have no odd cohomology, they commute. And so I don't know why. Maybe everybody knows the answer, or why people didn't ask last time. Then so we last time we used this construction with Z equals 0, and so maybe maybe everybody knows the answer, but as a rhetorical question, I can ask. So what are these operators for Z not equal to 0? Okay. And the answer. So the answer is was. So well, this is a slightly long story. So maybe I'll do this is the not sure what's the best way to tell it, but essentially, so maybe I'll write it. This was a conjecture. Was conjectured around, I don't know, 2007, 8, something like that, by Nekrasov and Shadashvili. That So these are operators of quantum multiplication. So quantum multiplication is some product which I'll maybe discuss in a second. That's a deformation of cup product, and it includes the counts of rational curves in your variety. And what they really computed, that was before. So this is before this quantum groups, before this kind of before our matrices. So this is slightly, like I said, this is the way it was slightly backwards. So this was before our matrix. This was before our matrices, before this quantum groups. Before everything, what they computed the spectrum. The first thing, well, of course, there in any line of mathematical development, there's always some stepping stones, and there were other stepping stones and so forth. So it's hard to say what was the first, but the crucial computation, I'll explain it at some due course. What Nekrasov-Tashvili computed, they computed the spectrum. And people don't realize that this computation was mathematical. It's a mathematically rigorous computation. If you depends on what you call, depends how you do what you call the operators of quantum multiplication. But depending on definitions, that is a rigorous computation. There's nothing to prove. It's not a conjecture that the spectrum is given. So that's a computation. So they computed spectrum in a beta ansatz form. So beta ansatz is some procedure. Beta ansatz is some procedure how people looked at this sort of integrable systems. Of course, ever since Baxter, or even in some sense before Baxter, but this point of the point of view that you should write quantum integrable systems in a form like this, that's the point of view of Baxter. Baxter noticed that Young-Baxter equation implies that this operator is commute, and also before Baxter, but I mean, Beta's paper is almost 100 years old. But even before Baxter, but certainly after Baxter, people. So this is there was kind of a form. There was some kind of industry of diagonalizing. A lot, not the industry. It was a lot of work. Lighting these Baxter's operators. And in particular, in that work, there's some schematics how you write what sort of equations you get for eigenvalues. And that's and Nekrasov-Tashvili noticed that the spectrum of the operator of quantum multiplication matches that description. So that's natural to conjecture that there is a quantum group, and such that the corresponding quantum integrable system is. So that's the meaning of the conjecture. So maybe to say it one more time, there's a long story of quantum integral systems, which was revolutionized at some point by Baxter, who realized the role played by Young-Baxter equation and in proving that things commute, and how to write commuting and how to use this commutativity to diagonalize this operator sometimes. That's been continued by many important works of many important people, and it's a well-developed field of science in which there is some notion of how you write Ansatz means something you try, so some substitution you try. So you write this ansatz for the eigenvalues, and then eigenvectors, and it's working if the parameters satisfy certain equation called beta equations. And so that's so Nikarashvili computed the spectrum of quantum multiplication. It depends. And if we talk about K-theory, it depends on definitions. What do you mean by? But in cohomology, this is unambiguous. I'll explain it in a second. And so then they computed that spectrum, and they noticed that this is given by equations that have this kind of absolutely definite Bethe-Ansatz form. And in fact, you look at this equation, you can more or less predict. Well, you can predict many features of your quantum group. But what would be because previously people know which features of the quantum group enter the beta equations. And so then this was the conjecture, and it's and something we're gonna. So in cohomology, this is so. And so maybe I'll close by defining, or maybe presumably all of you listening, I mean all of you on this current lecture, you know definition of quantum multiplication, but maybe some people who listen to the lecture or recorded lecture, they don't. And so then you can define. So defines. So in cohomology, one defines a new product. New, and it's important associative product. This is slightly unobvious product on cohomology of X by declaring that if I have three classes, maybe call them alpha will be my new product, maybe call it in red. So I take it, these are matrix elements of a new product where my alpha beta, the form alpha beta is just the integral over X of alpha cap beta. So this would be this, well, maybe I'll write it schematically. The sum of all sum over what? Sum over three-pointed rational curves that met. So if I have, this is my X. And so in my X, I'll have a rational curve of some degree D. Maybe some degree, maybe degree of that curve. This is an element in H lower 2 of X, Z. And then this curve will have to have three marks points that meet my classes. The point curve dual to my classes, alpha check, beta check, gamma check. So it's the curves that meet. And then here I put as place as a result of this count, I want to put Z to that degree. So this is a series. So in principle, a priori, it's a formal series. In the group algebra. of what? If you look at the effective cone, inside H2XZ. So in particular, so this some cone means not if I have a say a quasi-projective algebraic variety, then it's impossible for a curve, or just in general projective space, it's impossible for a curve and minus the same homology class to be simultaneously effective. And so this is a cone, and the tip of that cone, and the tip of that cone, these are curves of 0 degree. So I lost my cone. So it's a cone, and then there's a tip of that cone, which are curves of 0 degree that are points. When this is degree of my curve is 0, means C is a point, and so this expression here starts out as when if I have a point, then means I'm just counting triple intersections, and so I'm counting points that lie in triple intersection of my cycles. That means this my expression starts out with, which is the cup product plus O capital Z. And so it's a deformation. It's some operation that deforms the cup product. And the remarkable fact about it's associative, which is, anyway, I'm out of time, so I'm not gonna talk about this. But it's some family of operators that deform the operators of cup product. And what we're going to see, well, not see, but well, see. What we're going to see is that indeed the constructions we constructed so far, they directly relate to the enumeration of rational curves in this geometry. All right. So I apologize for going over time. I'll stop here. How about questions? Any questions today? Oh well. Then to be continued next week, and so there'll be, stay tuned for some announcements because we need to change the schedule to accommodate for other people's schedule in this fall semester. The semester starts, we'll have to do a change in schedule. All right, so I'll see everybody next week at a different time. Stay tuned for the announcement.